In this video, we'll rederive the kinematic equations which we introduced very early on in the course via the techniques of integration, specifically graphical integration. What we're going to do is assume the same context as we had when we introduced the kinematic equations, which is that we're dealing with constant acceleration. We also want to introduce the idea that we've put forward since then, which is that changes in velocity are accelerations times changes in time. In other words, acceleration is the slope of the velocity versus time graph. Correspondingly, the big change in velocity, in other words, the final velocity minus the initial velocity, must come from adding up all the small changes in velocity. In other words, adding up the area under the acceleration versus time graph for corresponding from and to endpoints. Integrating over time goes from time 0 to time t. Integrating over velocity is correspondingly the velocity at the beginning and the velocity at the end. This equation, we said before, can be interpreted just as a height function, which is the acceleration, times a little interval in width, which we accumulate over the total change. So in other words, this is the area under the acceleration versus time plot. Now, what would a constant acceleration look like? Well, it would be acceleration versus time from 0 to time t. If the acceleration were constant, then every little sliver of accumulated time would add a little bit of additional area under the curve until finally we got to the end and the total area under the curve had been added up from one side to the other. Well, what would the total area under the curve be? Well, that's simply a rectangle whose height is a acceleration in units of meters per second squared, and whose width is time t in units of seconds. So what would the area under the curve be? Rectangle, height times width. The area, height times width, would be a height in units of meters per second squared times a width in units of seconds for a total unit of meters per second. What does that say? It simply says change in velocity, v minus v initial, is area under the acceleration versus time plot, at. Units are meters per second, units are meters per second, that checks out. In other words, it's just our initial kinematic equation. Velocity is initial velocity plus acceleration times time. We can do exactly the same thing, graphing that equation and then taking the next step to changes in position. If we were to graph that equation, that was v equals v naught plus at, what would that look like? Well, that's the curve of a line. The vertical axis, v, in math mode, in high school, what do we say? Y equals mx plus b for the slope of a line. That's the vertical axis, y plus m. Oh, acceleration is the slope of the velocity versus time graph. Y equals mx, our horizontal variable, x is now time, actually. Y equals mx plus b. V naught is our y-intercept. V is our final velocity. And we have a slope of the line whose slope is a constant slope because we're dealing with constant acceleration in the kinematic equations, whose slope is meters per second rise over seconds run, in other words, meters per second squared, whose slope is the acceleration. What is the area underneath that curve? Well, it is a combination of a rectangle and a triangle. Each of those formulas is well known to us. The area of a rectangle is base times height. The area of a triangle because it can be thought of as half a rectangle, is base times height halved. What is this distance? Well, that's the initial velocity from 0 to v naught is the height of that. What's this height? Well, that height is v minus v naught, but we know that v minus v naught can also be written as at. What's the width of the graph? This is time from 0 to t. So the width of the graph is t. We know that delta x is the accumulation of small steps in x from initial to final. In other words, x final minus x initial. But dx is also velocity times small step in time. So in other words, delta x, change in position, is equal to area under the velocity versus time curve. Well, we have a velocity versus time curve for the case of constant acceleration drawn here. What is the area under the curve? That is equal to the area of the rectangle plus the area of the triangle. What was the area of the rectangle? Width t, height v naught. So that was v naught t. What was the area of the triangle? 1/2 base t times height at. In other words, what? X minus x naught is v naught t plus a t squared over 2. In other words, our familiar kinematics equation, sometimes written as delta x, or sometimes even just written as d, distance away relative to where you started.